In 4.2, we are looking at systems of linear equations in 3 variables. We have 3 objectives: to understand the geometry of systems in the 3 equations of 3 variables, to solve linear systems with 3 equations and 3 variables by elimination, to solve the systems with 3 equations and 3 variables in which some of the equations have missing terms, and then to solve special systems. The book has its own examples that you can read through, but what I want to point out is this particular figure right here. Okay, this illustrates the number of solutions possible for 3 equations with 3 variables. You could have 3 planes that intersect at a single point. You could have 3 planes that intersect at a line. You could have 3 planes that are common. An example of this might be and that's just one example. And then we have a situation where we have 3 parallel planes. You could have a situation where lines 1 and 2 are parallel, but the third, so planes 1 and 2 are parallel, but the third intersects both, in which you don't have any solution where all 3 planes have a point in common. You could have a situation where it makes basically a triangle, again, no points in common. Or you could have coinciding, where your first equation would be something like, your second equation would just be a multiple of that. And then your third equation would just be parallel to it. So these two are coinciding, and then this is a completely different equation. So you don't need to graph these out, but I think it does give you a depth of understanding to see the graphs. So the book goes through the graphs of the systems in 3 variables and then a procedure of how to solve a system in 3 variables. We're going to walk through a few examples, and I'm going to try to show you the graphs as well. Although you don't have to graph any of the equations in or any of the systems in 4.2, the equations in 3 variables, I do think it's helpful to look at a graph so that you can get a better understanding, a better depth of understanding of the content. So just to become a little bit more familiar with the Geogebra 3D graphing calculator, I'm going to graph x equals 1, and then we can confirm that the red axis is the x-axis. Okay, and then I'm going to graph y equals 2. And now we can see, so if you were looking at the normal Cartesian plane, the x-axis is horizontal, the y-axis is vertical, and there's y equals 2. And then our z-axis is the blue axis. Let me see if I can spin it around a little bit. Z equals 5. Sorry, this is not the easiest to control. So there's your z-axis, which would normally coming straight out at you for z equals 5, confirming that the blue axis is z. So let's take a look at some examples from 4.2, linear systems with 3 variables. I'm going to start out with number 3. These will take a lot of room, and I highly recommend that you line up all your x's, y's, and z's. If you are very neat and methodical about this, it will take a lot less time. So this is number 3 from your textbook. Now I'm going to tell you that I label these as row 1, row 2, and row 3. Your book just does it as a 1, a 2, a 3, but I use row 1, row 2, row 3. Okay, so now to solve these, essentially what I want to do, what I'm working towards, is getting the system rewritten so that it'll look something like this. Okay, so that first equation kind of looks like that. The second equation, I want to eliminate x. And the third equation, I forgot about h, I want to look like that. So basically you want kind of this triangular appearance when you go through the equal sign there. That's essentially what you're looking for. So to do that, I'm going to take row 2 and then subtract row 3, which is going to give me a row 4. Row 2, yes, you get to rewrite all of this. And then if I'm subtracting row 3, then I'm going to combine them. This eliminates x. Now I have 6y plus 2z equals 14. But I see here I can divide a 2 out, so I'm going to do that. And then my row 4 is actually going to be 3y plus z equals 7. So I used row 2 and 3. I haven't used row 1 yet. Now I'm going to want to use row 1. I'm going to switch colors. Row 1 minus twice row 3 to give me a row 5. So row 1 is 2x minus 5y plus 3z equals negative 1. And then negative 2 times this third row, negative 2x plus 4y plus 8z equals 10. And when I add those together, the x's are eliminated. I get negative y plus 11z equals 9. Now, if I was just going to rewrite this, I'd probably multiply by a negative 1, but my goal is to get towards a z equals. So I'm going to leave that, and then I'm going to take row 4 plus 3 times row 5. So row 4 was 3y plus z equals 7. And then 3 times row 5 would give me negative 3y plus 33z equals 27. You're starting to get an idea of why it's essential to line everything up. Then I have 34z equals 34, so z equals 1. So now, so far, my solution looks like x is unknown, y is unknown, but z is 1. So now I'm going to do what's called back substitution. And I suppose I can take row 4 here. and substitute the 1 in for the z. So then 3y equals 6, and y now equals 2. So now x is unknown, but y and z are known. So then I'm going to go back to one of the original equations. Let's go to y2, or row 2. Doesn't matter. And substitute both y and z. So then I get x plus 8 minus 2 equals 9. X minus 2 is 6, so if I subtract 6 from both sides, I get x equals 3. This means my solution set is one solution, the ordered triple, 3, 2, 1. The curly braces indicate my solution set, and then this is my ordered triple x, y, and z. So we have the red axis is the x, the green is the y, and the blue is the z. So that said, I'm going to go back and I'm going to enter the actual equations. 2x minus 5y plus 3z equals negative 1 was our first equation. Our second was x plus 4y minus 2z equals 9. And our third is x minus 2y minus 4z equals negative 5. So now when I look at this, my solution was x equals 3, which the positive x-axis is the red. Ooh, I don't know what happened here. I don't want z. There we go. We want 3 planes. So x equals 3, y equals 2. Let's put 2 up there. Y is 2, x is 3, and then z is 1. So I don't know if you can kind of see the intersection of the 3 planes there, right in there. So right in there is the intersection of the 3 planes. Our second example is 21 from the book. We have 2x plus y equals 6, 3y minus 2z equals negative 4, and 3x plus, minus 5z equals negative 7. I hope that you've noticed that I left a large space in and lined up the x's, the y's, the z's, the equal signs, and the constants. Okay? So this is row 1, row 2, row 3. I'm going to take 3 times row 1 minus 2 times row 3. So 3 times row 1 will look like 6x plus 3y plus 0z equals 18. And negative 2 times row 3 will look like negative 6x plus 0y plus 10z equals 14. And then when I add those two, my x's are eliminated. I have 3y plus 10z equals 32. If I look back at my original system, row 2 here, already has a y, z, -4, so x is eliminated. So I'm going to take row 2, and the coefficient is 3 there on y. The coefficient is 3 on y in R4. So I'm going to subtract row 2 from row 4. So I'm going to get -3y plus 2z equals 4, and then add that to the equation I just found. And when I combine those, y is eliminated. Now I get 12z equals 36, so z is 3. So now I can start my back substitution. If z equals 3, I suppose I can use any equation. 3y plus 10 times 3 equals 32. So then 3y, subtract 30 from both sides, is 2. Then y is 2/3. So far my x is still unknown, my y is 2/3, and my z is 3. Then I'm going to want to substitute both of those into an equation, and I'll just pick row 1 because I can. So 2 times x plus y was 2/3. There is no z value there, equals 6. Because I know we're fond of fractions, I will multiply both sides by 3. So 6x plus 2 equals 18. Then 6x equals 16. X then equals 8/3. So now my solution set, x equals 8/3, y equals 2/3, and z equals 3. You could go ahead and graph that in Geogebra if you wanted to see what that looked like, but since we've already seen 3 planes intersecting at a point, I'm not going to do that right now. What I'm going to do is move on to our next example. In 27 from the textbook, we are given row 1 as 2x plus 2y minus 6z equals 5. That's my row 1. Negative 3x plus y minus z equals -2 is my row 2. And then negative x minus y plus 3z equals 4 is my row 3. So in starting this, remember I want to eliminate x initially. I'm going to take row 1 plus twice row 3 rather, pardon. So row 1 looks like 2x plus 2y minus 6z equals 5. Twice row 3 would be negative 2x minus 2y minus 6z equals 8. And then when I add these together, I've eliminated my x's, my y's, and my z's. So now I have 0 is equal to 13. That's a false statement. Therefore, this is called inconsistent. And I'll show you what that looks like. I went ahead and entered the 2 equations that we used, row 1 and row 3, into the Geogebra 3D calculator, and I've orientated the x-axis, the red axis, and the y-axis was the green axis, z is the blue. So right now, if we're looking at it a Cartesian plane, like we'd normally graph, we don't see a whole lot. Trying to spin this. as I spin so that the z-axis is upwards, you can see that you in fact have two parallel planes. So that's why the solution is, that's why it's called inconsistent. There's going to be no solution between those two planes. They're parallel. So that's as far as you would need to take it for the homework. But I went a little further because of my curiosity, and I wanted to know whether we had three parallel planes or whether we had, I mean, there's a lot of possibilities for inconsistency. We could have three parallel planes. We could have no points in common, where you could have one plane intersecting the two parallel planes. Or we could have a situation where the third equation is going to be a similar or just an identical first or second equation. So I wanted to see which of those cases we had. So now I've used lines 1 and 3. I'm going to use line 2 now. If I take row 2 minus 3 times row 3, I have negative 3x plus y minus z equals negative 2, and then 3x plus 3y minus 9z equals negative 12. And when I add those to eliminate, I get 4y minus 10z equals negative 14. This tells me that it's not going to be parallel to the other two planes. So I want to see what that looks like because I'm curious. We saw that the two inconsistent lines were row 1 and row 3, which we can see graphed here, and I did figure out how to change the colors. So this is what we were looking at a moment ago, were the two planes that were parallel. And I added in row 2, and we can see that it is a single plane that intersects two parallel planes. Again, there's no solution, so it's still inconsistent, but my curiosity, I wanted to know which of these examples it looked like. So it's like example E here. The system that we just examined algebraically or solved algebraically might remind you of the theorem that we learned in 6.3, which read, if a plane intersects two parallel planes, the lines of intersection are parallel. So hopefully that image jumped in your mind, which is like example E here, and is a visual representation of problem number 27. I'm going to move forward to problem number 33 from our textbook. So we have 2x plus y minus z equals 6. That's my row 1. 4x plus 2y minus 2z equals 12 is row 2. And then row 3 is negative x minus 1/2 y minus, plus 1/2 z equals negative 3. So looking at this, I want to eliminate x. I'm going to combine rows 1 and 3. In fact, I'm going to take 2 times row 3 and then add it to row 1. I just put that on top because the fractions were there and I felt it was easier for me. It doesn't really matter which one goes on top. So now when I combine these, my x's, my y's, and my z's are all eliminated. In fact, my constants are eliminated. So this indicates that row 1 and row 3 are the same plane. Let's take a look at the graph. So I went ahead and entered all three equations and somewhat orientated the positive x-axis and the positive y-axis. So now when I show the first equation, it's shown in green. When I show the second equation, it's shown in orange. The way this graphing calculator does it, it kind of splits them. But as I move this, you can see that there is in fact only one plane that's graphed. So the gray is just to kind of orientate us. That's the normal piece of paper 2D graph that you would be used to. This is this plane here is the plane generated by equations 1 and 3. So when I activate the third plane, you can in fact see that all three equations are going to generate the same plane. Let's do that algebraically. Returning to the work that we were doing, I've used row 3 and row 1. Now I'm going to take a look at row 2. In fact, if I divide row 2 by 2, I can see that it's identical to row 1. Now I do know, in fact, that all three equations are representative of the same plane. There are infinite solutions, and we would write that the curly braces indicate the solution set. The solutions will include any x, y, z pair such that, so you need the vertical line there, fits the equation, and then you pick one that's closest to standard form. So I'm picking row 1 here. Row 4 I can still factor the 2 out of. Row 3 here I have fractions and the coefficient, leading coefficient of x is negative. So I want a positive coefficient of x and everything else to be integers. So y minus z equals 6, and then I close my curly braces. So on a test, this is what you would have to write as the solution set for this particular system. In our final example, number 37 from the book, we have x minus 2y plus 1/3 z equals 4, and then 3x minus 6y plus z equals 12, that's my row 2, and negative 6x plus 12y minus 2z equals negative 3, that's my row 3. So if I look at 3 times row 1, wouldn't that give me row 2? Therefore, we know that row 1 is equal to row 2, so that's going to be the same plane. And then if we look at combining rows 2 and 3 now, I'm going to take negative 2 times row 2 and add that to row 3. So that's going to give me negative 6x plus 12y minus 2z equals negative 24. And for this final row, I can see here that x, y, and z would be eliminated. Now, are they the same? If they are, this equation will be equal. If they're parallel, then you'll have something like 0 equals a number. If I were truly going to eliminate, I would want the signs to be opposites. And then from row 3, we had a negative 3. So here we have 0 is equal to 21. Because that's not true, that means we have an inconsistent system here, which means these two are parallel. Well, we already know that row 1 is equal to row 2. That's the same plane. So that would be parallel then to row 3. And let's take a look at that graph. So here I've entered the 3 equations from problem number 37 in our book, and none of them are activated at the moment. So this gray field is the piece of paper. If you were graphing on an XY axis, remember red is X, Y is green, and the gray is like our piece of paper. If I activate that first equation, I can see the single plane. When I activate the second equation, algebraically we determined that that was the same plane, and that is confirmed by the graph. And then algebraically we suggested that equation 3 was a parallel plane, also confirmed by the graph. So this is reminiscent of example G here, where equations 1 and 2 are indeed the same plane, and the third equation is a parallel plane. If you found this video helpful, please like and subscribe. Smash that like button. You know you wanna. Come on, give it a thumbs up.